Hello. In this video, we're going to have a look at problem 2300, successful pairs of spells and potions. In this video, we're going to practice the use of binary search. First, let's look at the problem statement to digest the requirements. Here, we are given two positive integer arrays called spells and potions of length n and m, respectively. Here, spells I represents the strength of the S spell, and the potions G represents the strength of the G's potion. We are also given an integer called success. So a spell and potion pair is considered successful if the product of their strength is bounded below by success. So we are required to return an integer array called pairs of length n, where pair I is the number of potions that will form a successful pair with the S spell. So before we look at the example, let's first look at the constraints. First, n and m are the lengths, so they are bounded above by 10 to the power 5. So 10 to the power 5 is a decent large number, which defines the problem size. And the last two constraints are assumptions on the elements in spells and in potions, and also the range on success. So with that said, let's look at the examples. So here we just look at example 1, and for spell 5, right? So here the success is 7. So if we check 5, so we have 1. 1 times 5 is 5, less than 7, no successful pair. Then once the potion values is larger than 1, because they are integer, so we have 5 times 2 is larger than 7, so also the remaining ones. So we have four successful pairs for this spell, right? So this is about the examples. So now let's look at the explanation or strategy. So here actually we can think of sorting. So as for each spell, we are interested only in the number of potions that can form successful pair with the spell, right? Now we can fix a spell, and then we can find those potions such that the potion times spell is greater than or equal to success. In other words, the potion should have a value greater than or equal to this number, success float division by spell. So here we use this one. So we can sort the portions, and as such we could find the insertion point or index for success spell in portions using binary search. Using this index, so we can get the number of pairs for the spell in portions, right? In other words, we can find those potions that can form successful pairs with the given spell. So with that said, let's look at the coding. So once we digest the idea, so writing the code is sort of a routine task. So first, I'm going to make some preparation. So here, n and m will be the length, right? Spells and the potions. And then what we're going to do, so here actually we just maybe not used. Let's say we can do the sort for potions. So we sort from small to large, right? And then this is one thing. Another thing is that I would like to write a function to do the above job, or as here, right? So here we can define a find number of potions. So here we accept a integer value or spell C, and then what we are going to do is to return the number of potions that can form a successful pair with the given spell. So here actually we can do binary search. So here we use this module called bisect left. And what we are going to do is we are going to check insertion point in the sorted portion. So we can assume that this is already sorted. So we can do success over the spell. So this the spell is given, right? By assumption, this spell is always negative, is always positive. So this is the value we check for insertion point. So we are going to get an IDX, right? So notice that this bisect left, what's the mean? It means that portions I strictly less than success spell. If I is less than the IDX, right? So with that said, so the proper ones will be the length of this portion, right? The portion is m, so we use m minus the IDX. So this number, m minus IDX, is the number of portions that can form successful pairs with the past spell, right? So this is the one part. So next, so what I'm going to do, so here I don't think I need this n, so let's just delete that. Step 2, step 1, I guess. So then do the return. So we can use the map function to map this callable function name portions to the spells. In other words, we apply this function to each element in this iterable, right? So actually we can directly return this if we are not that rigorous, because here we are return a iterable. So here we require a list of integers. Anyway, let's first check this form. Yeah, it passes one example. So now let's look at the generic case. Yeah, it passes all the cases. So this is a one return format. If we want to make sure we return as marked here, so we can do a list conversion, right? Let's check again. Yeah, it passes all the cases. So before we end this video, let's make a comment on the time complexity. So here we assume that this n is the length of the spells. So for this part, the time complexity is m logarithm m, right? So this is the sort algorithm. So let's let me put it here. So this is the one part. So now the spells has so the portion has a length m, right? So each time we do this one, so this function is what's the time complexity, because it's a bisect. So it's we have already sorted the portions. So this one will be logarithm, right? Logarithm of n m. So m is the length of this portion, right? So here we call n times, right? This function, because we apply each time with one element in spells. So overall, so we have m times logarithm m, then plus n times times logarithm m, right? So overall it should be n plus m times logarithm m. So if we like, so we can use see, this is roughly this, or we can use big O notation. So let's do this. Yeah, with that said, I guess that's about it for this video.